All right. So this question was posed yesterday on one of my AP Chemistry teacher listservs by the people who grade the exam. So I've been mentioning how they know for a fact that they will not accept credit for that. So when we're doing the partial pressure and we're plugging it into the Kp expression, remember you only do gases, but those brackets right there are inferring molarity. Not inferring it. They're saying you got molarity. You cannot use brackets for anything other than that. And so what the teacher showed was if you type it, you get that nice curved parentheses, and they say that this is okay. It's okay to put parentheses. And I did mention that, but you notice I don't do that. I don't put the parentheses because the reason they said is, now look at this one. So now you still have a curve in your parentheses because again, you're going to be writing this. So now when the curve starts to come out of the parentheses, at what point do parentheses become brackets? That's the issue. So why even give them the temptation to not give you credit? So just don't use brackets. So the best way that I suggest to do this Kp expression, it would be NO2 squared over the pressure of N2O4. No parentheses, no brackets, no worries about anything else because you don't need it. You can still do the, and then if we had another one, let's say we had times another gas, you know, we don't need parentheses. We don't need brackets. I would suggest not using them. All right, so I want to go over the exact problems that we are doing today. So that way you have this, you can kind of work along together with me as if we were in class. And hopefully we will be soon enough. All right, so consider, let me pause for 1 second. I gotta pause for 1 second. I have to grab something. Okay, I just wanted to grab my paper because I already did these numbers. That way I don't have to do the math again. All right, so consider the equilibrium. So what I did was I rewrote the equation right here just to make it a little easier for me to do a nice chart. So we have I, C, and E. Remember, initial, the change, and the equilibrium. And we are given the Kc, or we're looking for the Kc. So remember, we are going to use brackets here because we do want molarity. We are using molarity in this one. But we're not given molarity right off the bat. We're given 3 moles of NO are introduced into a 1 liter evacuated flask, NO. So that means there's none of this and there's none of that explicitly stated in the problem this time. I wrote these are more like AP questions. And so when we divide now 3 moles by 1 liter to get the molarity, we get 3 molar. Sometimes they'll use 0.5 liters, sometimes they'll use 0.25 liters, and sometimes they'll use 2 liters, just to make the math kind of easy. But in this case, they made it really easy because they made it 1. All right, so when the system comes to equilibrium, 0.755 moles of N2O has formed. Determine the equilibrium concentrations of each substance and then calculate the Kc. All right, we know this reaction has to go from right to left because we don't have any of the N2O or the O2 to start with. And so it can't go to the right. Minus 4x stoichiometry plus x plus 2x. So at equilibrium, this is 2x, this is x, and this is 3 minus 4 times x. Now, this would be a case of about the easiest one we can do because we're given now one of the equilibrium concentrations. The N2O, it says, there's 0.7 at equilibrium. So down here at equilibrium, now again, that's moles. I'm dividing by 1 liter to get molarity. And as I said, what I like to do is actually circle that or box that and know that that is the correct molarity that I'm going to use for N2O. Now that's equal to 2x. So divide that by 2 and you get 0.378 molar for x. So just that divided by 2. So then multiply x times 4 and do 3 minus, and you get 1.49 molar for the NO. All right, so now we have our equilibrium concentrations. Now the Kc expression, NO to the 4th, I would do this every time. Get in the habit of doing it. It always gets you a point. Equal, so now we know the numbers. 1.49 at equilibrium to the 4th, 0.755 squared, and 0.378. And that gives us a value of 22.9. Unitless. So no units on the values for K. Unusual for us to not have units. All right, so number 2. So once again, I rewrote the equation for you to make it easy for you to do your ice chart. All right, what are we given this time? This time we're given the K value, so 5.5 times 10 to the third. If the initial concentrations of each species are, all right, this time we have molarity, 0.1 molar, Br is 0.2 molar, and HBr is 8.5 molar. So first, letter A, proceed which direction it will proceed, write the Kc expression, write an ice chart, just don't solve for X, and you'll see why when we get there. All right, so which way is it gonna go? So the way we figure out which way it's gonna go is we find the reaction quotient. That's what Q is called. And we got to figure out what Q is so we can compare it to K. And the way we do that is you just plug them in. So we have HBr, which is 8.5, but it's squared, right? Coefficients become exponents over 0.1 times 0.2, both to the first power. When you divide that, you get 3613. Now the K value is 5,500 according to our value up there. So Q is less than K, which means we need more products because we need Q to go up to equal 5,500. So this thing is going to shift to the right. So there's how we figure out which direction it's going. So letter A, which way is it going? It's proceeding from reactants towards the products to the right. Write the Kc expression. All right, so the Kc expression is the products, HBr, we only have one product. Coefficients become exponents, reactants, and you just multiply. And then the ice chart. So what is our ice chart going to look like? Well, we now know that this thing goes from left to right. So this is minus x, and this is plus 2x. So you get 0.1 minus x, you get 0.2 minus x, and you get 8.5 plus 2x. All right, now, as I said, don't solve for x, because if I do continue this on, we now have 5.5 times 10 to the third equals 8.5 plus 2x squared over 0.1 minus x times 0.2 minus x. So we'd have to FOIL that. This is not a perfect square. Now, if I had made the initial concentration 0.1 and 0.1, then we would have 0.1 minus x on the bottom squared, and then we could take the square root of both sides. And that is an available question for me to ask. But in this case, we would have to solve the quadratic, and we're not going to be asked to do that. I'm not going to ask you to do that, and nor will the AP test. All right, moving on. Number 3. All right, so once again, we're going to do an ice chart. I wrote the reaction for you here to make it a little easier. We're given a particular temperature. Now we have 2.7. So here again, we have moles, not molarity. And so we do have to find the molarity. So 2.75 divided by the volume 4.5 gets you 0.611 molar to start with. Previously evacuated. So none of that, none of that. It has to go to the right. Minus 2x, though, according to the stoichiometry. Plus x, so x and x. The Kc expression equals H2 times I2 over HI squared. All right, let's plug in our values and solve for x. So we have x times x on the top, x squared, and then we have 0.611 minus 2x squared. So there's a case over here where we have a perfect square, which means I can now take the square root of both sides. So the square root of x squared, the square root of 0.6 minus 2x squared, and the square root of 0.049, which is 0.221. Solve for x. And x equals 0.094. Yeah, so just you can do the algebra. And if you need some help with the algebra, don't be shy. Come and ask. I can help you. I can show you how to do these. Make your life a little easier. So then 0.611 minus 2x, we got 0.423 molar. Remember what I said about this? I like to write these over here. Not only going to write that one once, since they're both x. All right, and then the last one. So the last of the types that we learned. So we have to know. Now, the ones I skipped are the ones that are already at equilibrium, where you don't have initial conditions. You already have equilibrium, where you just plug them in. They're way easier. All right, so once again, and ice chart. So given the following reaction for acetic acid, so CH3COOH, there's that carboxyl group, acetic acid, the organic way to write acetic acid. Watch this one right here, pure liquid. Remember about pure liquids and pure solids. We don't include those. So this right here is not included in our ice chart, pure liquids and pure solids. And they're not even included in our K value either, remember, Kc. All right, what are we given? We're given a 2.25 molar solution of acetic acid is allowed to reach equilibrium. So we're starting with 2.25 molar, means we don't have any of that or any of that. So we're looking for the equilibrium value of the H3O plus. So this is minus x, 2.25 minus x, plus x, x, and x. Our Kc expression. And we're getting in the habit of writing it right away. H3O plus, the products over the reactant. So there's our K expression. Plug them in. We got a K value, 1.75 times 10 to the minus 5 equals x times x squared over, not 0 there, minus x. All right, so we'd have to solve the quadratic equation here. We don't have a perfect square, so we're not at equilibrium. We don't have a perfect square, and we're not given one of the equilibrium concentrations. So how are we going to find this one? Well, this was the last of the type we did where, look how small K is. Look how small K is, times 10 to the minus 5. Whereas our concentration is times 10 to the 0 power. So we have a difference. So there's the equilibrium constant. And here's our concentration. So, if we added more zeros to make them the same, we're talking all the way to that decimal place before these two match up. So the way we've described that is there's an order of magnitude difference of 5. And so what I showed you yesterday, so this is the key step, is since x is going to be so small because K is so small, we ignore it. And that makes the algebra actually really easy now. If we look at, let me erase some of what I said, get back to the calculation here. So we're ignoring now the minus x. So now all I have to do is multiply both sides by 2.25 and then take the square root. So, and x ends up being 6.27 times 10 to the minus 3. And that equals then the molarity of the H3O plus. So that's letter A. All right, now when we did this, what I said you have to do is check the 5% rule and see if this is a valid assumption. Because if this number right here, this minus x that we ignored, is 5% or more of the initial concentration that you ignored it from, then it's not valid. Then you do have to solve the quadratic. Now, we're not going to have to do that, but we should check. So what you do is you take the x value that you got, divided by the initial concentration. So remember that number right there. Or you could look at it as, the number here and the number that we tried to subtract. And then times 100, and that will give us a percentage. And this is called the percent ionization. So that's actually what we're solving for here. When we're checking the 5% rule, the 5% that we're talking about is 5% ionized. Is it 5% ionized or more, or is it less than 5? And that's what we need, and you'll see when we do this one. So if you do that value there, 6.27 divided by 2.2 times 100, or my preferred way, which I showed you, is x over 100. You know, solve that way to find a percentage. Either way, you get 0.3%. So you can see it's a really small amount, 0.3%, way less than 5%. And then letter C, what is the pH of the solution? So I give you the formula. So pH is equal to the negative log of the H3O plus. And this is actually, after this unit, all we have left, the only big thing we have left is pH. pH, acids, bases. And it is related to equilibrium. So now we know what we got for the H3O plus, so it's right there. So just take the negative log of that number, and it comes out to be a pH of 2.2. This would be about the concentration that you have, actually maybe a little less, of acetic acid in an actual vinegar solution. Vinegar we know is acetic acid. It has a pH of about 2.2. All right. Again, any questions, let me know.